the rate constant for the first order decomposition of a certain reaction is given by certain expression, and you have been asked to find the activation energy, rate constant at 500 Kelvin, and in the third question we have to find out the temperature at which the half-life period of the given reaction will be 256 minutes. So, the expression that is provided to us is once again based on the Arrhenius equation. It's a previous JEE equation. We have the Arrhenius equation applicable in terms of the logarithms, where we are given the log K as 14.34 minus 1.25 into 10 to the power 4 upon temperature in Kelvin. Now, when we are given this expression, we will map it with the Arrhenius equation and we take the existing values. What I mean to say, that when I write this as natural logarithm of K, we are going to write it as natural logarithm of A minus EA upon RT. Now, when these two equations are mapped with each other, it is clearly indicated that natural logarithm of A is 14.34. From this data we can find out the value of A, and here the slope can be taken in order to find out the activation energy of the given reaction. So, here you can see that this is the straight line which is passing with a intercept and the slope being negative, whose value equal to 1.25 into 10 to the power 4. So, now when I substitute here the R value, I am going to get the activation energy for the given reaction. Suppose I am substituting this in kilojoule, I will be getting my answer in kilojoule. So, here the activation energy for the given question is the first answer, that is 24.83 kilocalorie per mole. So, when I wish to obtain this value in kilocalorie, what I will do is, instead of substituting the R in kilojoule, I would be substituting the value of R in kilocalorie, that is 2 into 10 to the power minus 3 kilocalorie per mole. So, this is your first question answer. Then we have to find the rate constant at 500 Kelvin. So, over here, when we substitute the temperature in the given expression, since we have obtained the activation energy value, when I am substituting here the temperature which is provided to us, that is 500 Kelvin, I will be able to find out the K after the application of the anti-logarithm. So, here the answer for the calculation of K is 2.35 into 10 to the power minus 5 second inverse. Then, as a part of the third question, you have been asked to find the temperature at which the half-life period of the reaction will be 256 minutes. So, here when I substitute the K value, that is, if it is a first order reaction, 0.693 upon the T half of the reaction is given as 256 minutes. So, when I am substituting here the T value, you can see here the T half is being mentioned as 256 minutes, which I am going to convert into second, which is equal to 14.34 second inverse minus 1.25 to 10 to the power 4 divided by T. So, you have been asked to find the value of T in this case. It's a very simple question, previously asked in IIT-JEE, and in each case you have to find one variable, and the answer for the third question is to find the value of T, which is turning out to be 513 Kelvin. So, here in this question, in every question there is one unknown or variable which is being asked. In the first question we got the value of EA after the substitution of temperature. In the second one we have substituted the temperature to find the value of K. In the third one we have substituted the T half value to find the temperature. Then we have the decomposition of Cl2O7 at 400 Kelvin in the gas phase into Cl2 and O2, which follows first order kinetics. It is given that after 55 seconds at 400 Kelvin, the pressure of Cl2O7 falls from 0.062 to 0.044 atmosphere. Then you have been asked to find question 1, the rate constant, and question 2, the pressure of Cl2O7 remaining after 100 seconds. So this question is based on the kinetics of the gas phase decomposition reaction, wherein you have been given Cl2O7, which upon thermal decomposition giving rise to Cl2 and O2. Now, since we are dealing with the pressure changes, first of all, it is our duty to balance this equation, and we can see here that the pressure after 55 seconds, the Cl2 pressure is falling from 0.062 atm, that is atmosphere, when these two are nothing, to 0.044 atmosphere over a period of time. And it is given that it is 55 seconds during which the pressure of Cl2O7 has been changed. Now, since we know the initial and final pressure of the reactants, we are going to find out the K value by using the first order kinetic equation, 2.303 by 55 time log of the initial pressure of the reactant or concentration divided by the final pressure. So this data will be useful in finding out the value of K for the given reaction. Then in the second part of this question, you can see that we have been asked to find the Cl2O7 pressure after 100 seconds. But you know, my dear student, that the K value which we are going to obtain here is not going to change, which is calculated as 6.23 into 10 to the power minus 3 second inverse. It remains the same. So when I substitute here the K this time, which is equal to 2.303 by T, that you have to find out when the, or you have been asked to find the pressure of Cl2O7 after 100 seconds. So what I mean to say, that you have been given the time course of the reaction, this time as 100 seconds, and you have to find out the pressure of Cl2O7 after 100 seconds. That means simplification of this equation will fetch you the value of pressure of Cl2O7 after 100 seconds as 0.033 atm, that is atmosphere. A first order reaction is 50% complete in 30 minutes at 27 degrees Celsius, and the same 50% is finished in 10 minutes at 47 degrees Celsius. Then you have been asked to calculate the rate constant for the reaction at 27 degrees Celsius and 47 degrees Celsius separately, and you have been also asked to find the energy of activation for this reaction. So the data indicates that the T half of the reaction at 27 degree Celsius, or 273 plus 27, that is 300 Kelvin. Directly I am writing here the half life of the reaction at 300 Kelvin, which is mentioned to us as 30 minutes, and the T half of the same after 47 degrees Celsius, that is 320 Kelvin, is mentioned as 10 minutes. Then you have been asked to find the rate constants for the reaction at 27 as well as 47. Because this is a first order reaction, you know that K at 300 Kelvin is 0.693 by T half, and K at 320 Kelvin is 0.693 upon 10. So this many minute inverse is going to be your answer for the question. So here when we simplify this, we are going to get 2.3 into 10 power minus 2 minute inverse, and this as 6.93 into 10 to the power minus 2 minute inverse after the simplification. Now to find the energy of activation, we have log of K of 320 upon K of 300 is equal to energy of activation upon 2.303 times of R into 1 upon T1 minus 1 upon T2, where we know that since we have the values of what you call K1 and K2, when I substitute here, I am going to get 6.93 into 10 power minus 2 upon 2.3 into 10 power minus 2 is equal to energy of activation. Suppose I am willing to find this energy of activation in kilojoule, I will be substituting the R value as this much, 8.3 into 10 power minus 3. Now since we have the temperature values, the initial temperature is 300 and the final one is 320. Now after simplification, the energy of activation for this question for part 2 is obtained as 43.85 kilojoule per mole. For the reaction where 2 moles of nitric oxide is reacting with H2 in gas phase to give you the N2O as well as H2O, and a pressure of H2 as 147 torr. Then you have been asked to determine the order of the reaction with respect to the NO as well as H2. In this case, if I assume that the rate constant for the given reaction is K minus dP by dt, that is the rate with which the reactants are reacting, or the change in the pressure or the decrease in pressure of the reactants per unit time is K times, that is the rate constant, into partial pressure of NO whole power some coefficient and partial pressure of H2 whole power the coefficients. Now we have been asked to find the values of A and B in this question by providing the rest of the values. Now you can see here minus dP by dt was found to be 1.5 torr per second. This value is mentioned to us. K is a rate constant. When the pressure of NO was taken to be 359 torr whole power A, and here the pressure of H2 is remaining constant, because in the next case the minus dP by dt was found to be 0.25 when the pressure of NO has been changed to 152 torr, H2 being kept constant. Now when I have got these two equations, now when I am dividing these two, the pressure of H2 being cancelled along with the rate constant, and we know that 1.5 upon 0.25 is equal to 359 by 152 whole power A. Now during the simplification, when I apply logarithm, you can see log of 1.5 by 0.25 is equal to A times log of 359 upon 152. So this will fetch you the value of A upon simplification. Here when you simplify this, you are going to get the value of A as 2. Now this we made use of the data related to this NO to find the value of the order of the reaction with respect to NO. Now in the next case, I will be utilizing the same equation again, wherein the pressure of H2 had been changed by keeping the pressure of NO constant, and various rates are given about this reaction. So we have 1.60 torr per second as the rate. When the pressure of NO is made constant, already we got the value of A, but since I am knowing the value of A, I will be writing it as 2 into partial pressure of H2 in the first case is taken as 289 torr. Order of the reaction with respect to H2 is assumed as B, and it was found to be 0.79 torr per second when the pressure of H2 is made 147 torr. Now when I have got these two equations, once again I will be dividing these two, wherein this entire term gets cancelled, and once again I will be using the logarithm to get the value of B. Simplification of this equation, calculation would fetch us the value of B, which is obtained as 1. So therefore the answer for this question is option C, where the orders are calculated. How many times will the rate constant of a reaction proceeding at 300 Kelvin increase if the activation energy of reaction is lowered by 5 kilojoule per mole? The question is to find the ratio of the rate constants by using the Arrhenius equation. Say rate constant is K1 when the activation energy for the given reaction at a given temperature is EA, and the temperature is given to us as 300 Kelvin. So when I substitute the temperature here after knowing the equation, you can see that temperature had been kept constant throughout. So it is 300 R. Now in the second instance, what we did is we have decreased the activation energy of this reaction by 5 kilojoule without making any change in the temperature. Then you have been asked to find the ratio of the rate constants. Now when I do this, you know that the collision factor is not going to change when you have altered the activation energy by providing any catalyst. So when you have taken the ratio of these two, you can see that you are going to get this as this much. Now you are going to get K2 by K1. Your activation energy got cancelled. So therefore, when I am using the logarithm, that is base E, which is equal to 5 upon 300 times of R. Here this activation energy is decreased in kilojoule per mole, hence we will be using the R value once again in kilojoule per mole. So when I simplify this expression, I will be getting the ratio of K2 by K1, by which I will be observing that the rate constant is increased 7.4 times, hence option A is the correct answer. For a reaction between A and B, you have been given the data. I mean to say it is regarding the concentrations of A and B mentioned in mole per liter, where the rate of the reaction is given at two different temperatures. One is at 300 Kelvin, the other is at 320 Kelvin. Then from this data, you have been asked to find the rate of reaction at 290 Kelvin when the concentration of A being equal to 0.001 molar and that of B is equal to 0.002 molar. So in the given question, first when you write the rate law to find the order of the reaction initially, because you have been given the rate constants can be obtained here or the orders can be obtained first. You can see that when I take the rate constant as not changing at a particular temperature at 300 Kelvin, you can see that different rates are given. As I supposed to write this as directly proportional if I don't want to indulge the rate constant in a given equation. So what I mean to say that initially I will be finding out the orders of the reaction. You can see the first data, what we did in that is we have multiplied the concentration of A two folds. You can see the concentration of A is increased from 2.5 into 10 to the power minus 4 mole per liter to 5 into 10 to the power minus 4 liter. And also we have doubled the concentration of this B, then rate is increased by 8 folds. You can see it is changing from 5 into 10 to the power minus 4 to 4 into 10 to the power minus 3, that it is increased by 8 folds. Now in the second case, when I have increased the concentration of A from 5 into 10 to the power minus 4 mole per liter to 1 into 10 to the power minus 3 mole per liter, that means when I have doubled the concentration of A by keeping the concentration of B constant. You observe the second and third data. It's given that the concentration of A is doubled by keeping the concentration of B constant, then rate is increased by 4 folds. That means clearly it is indicating that the order with respect to A is 2. Or else you substitute in the given data. At 300 Kelvin, what we all know that the rate is 5 into 10 to the power minus 4, which is directly proportional to concentration of A being 2.5 into 10 to the power minus 4 whole power A, and concentration of B being equal to 3 into 10 to the power minus 5 whole power B. And the second one is 4 into 10 to the power minus 3, which is directly proportional to the concentration of A being 5 into 10 to the power minus 4 whole power A. This is 6 into 10 to the power minus 5 whole power B. In the third case, we have 1.6 into 10 to the power minus 2, which is directly proportional to the concentration of A is increased 2 folds, 1 into 10 to the power minus 3 whole power A, by not changing the value of B. Now when I have divided this equation, you can clearly see this ratio clearly indicates that it is increased 4 folds when the rate of the reaction is doubled. So when I simplify this, I am going to get the value of A as 2. Now after substituting the value of A over here, I will be getting the value of B as 1. That means the order with respect to A, reactant A is 2 and that of B is 1. As I told you directly, also we can do by looking at the data which is provided to us in the question. The second and third data clearly indicate that B has been kept constant. By doubling the concentration of A, the rate is increased 4 folds. This time 2, this time 4. That means 2 square will become equal to 4 times of the rate. That means by taking the rate as 4 folds, we might have increased the concentration of the reactant 2 folds, possible only when this is raised to the power 2. That means the order with respect to A is 2. And you can see from the first 2 data, I mean to say 2.5 into 10 to the power minus 4 of A and 3 into 10 to the power minus 5 of B, and 5 into 10 to the power minus 4 of A and 6 into 10 to the power minus 5 of B, you can see that the rate is increased by 8 folds. Already you know that with respect to A it is turning out to be 2, and this side I doubled and this side it is becoming 8 times. That means it is becoming the power 3. 2 to the power 3 is equal to 8. Already we know that the order with respect to A is 2, so therefore the order with respect to B will be 1. Now this is how we are going to find out the order, or you have the conventional methods to find the order as well. Now after knowing the order of the reaction, we have to find out the rate constant. Now we know that at 300 Kelvin only I am doing all these calculations. You can see I have the data with me. Now K at 300 Kelvin, since we have that value, 2.5 into 10 to the power minus 4 whole power 2, 3 into 10 to the power minus 5 whole power 1. Now from this data, we have to find the K at 300 Kelvin. That means you have to find out the rate constant at 300 Kelvin. And also you have to find the rate constant at 320, because you are given the rate at 320 as 2 into 10 to the power minus 3, which is equal to K times of 2.5 into 10 to the power minus 4 whole power 2, 3 into 10 to the power minus 5 whole power 1, or else you can directly find the ratio of the two. The ratio clearly indicate that K320 by K300 is equal to 2 into 10 to the power minus 3 by 5 into 10 to the power minus 4. Now when I substitute in the Arrhenius equation, log K320 by K300, that is 2 into 10 to the power minus 3 by 5 into 10 to the power minus 4 is equal to energy of activation upon 2.303 R into 1 by 300 minus 1 by 320. So from here I will be finding out the value of the energy of activation. Now after knowing the value of energy of activation, you have to find out the rate of the reaction at 290 Kelvin. So therefore you have to find out the rate constant at 290 Kelvin, for which I can use this data. What I mean to say, I will keep this intact to find the value of the EA upon 2.303 R by substituting the log of this. Now what I will do, carefully observe, we have got the values of A and B as the first question, then we have substituted here in the expression the values of A and B to get the ratio of K320 and K300, and we have used the Arrhenius equation integrated to get the value of this. Now we know that log K of anything you can take, either 300 or 320, but ultimate task is to find the K of 290. But you know that EA by 2.303 R, whichever you are going to find out from there, is going to remain the same. The same value you will be substituting here into 1 by 290 minus 1 by 300. So by substituting this value, already we know the K300, we have calculated that value. After substituting K300 and EA by 2.303 from this equation, you have to get K at 290 Kelvin. So finally rate of the reaction which has been asked to you is equal to K at 290 Kelvin into concentration of A 0.001 whole square and concentration of B 0.002 whole power 1. That means by substituting K at 390, you will be getting the rate at 290 Kelvin as 0.248 mole per liter second inverse. We have arsine that decomposes on heating to arsenic and H2 gas. The decomposition is studied at constant volume and temperature, and the data is provided to us. And we have been asked to find the velocity constant assuming this reaction to be first order. So we can use one data or many which is provided to us to find the value of K, that is nothing but the velocity constant. For that you have to first write the decomposition of arsine gas. Upon decomposition, you know that you are going to get arsenic metal and H2 gas. Now initially when we begin this reaction, we know it's given that the pressure in atmosphere is 0.9654 when we don't have any H2 in the reaction. It's given that after 5.5 hours, let's assume that the pressure of arsine decomposed is X atm, then the remaining will be 0.9653 minus X. Now for every 1 mole we are getting 3/2 mole of H2, hence decomposition of X atm pressure will fetch you 3x/2 atmosphere of H2. We are not concerned about arsenic here because the vapor pressure of arsenic is negligible, and because as it is present in the solid phase. Now we know that after 5.5 hour the total pressure is found to be 1.06 atm. So 1.06 atm, the total pressure is equal to sum of the partial pressure of all remaining gases, that is the pressure of arsenic and pressure of H2 gas. Now when I simplify this equation, I will be getting the value of X. After finding out the X value, if it is a first order reaction, the velocity constant or gas constant here is 2.303 by time of the course is 5.5 R, logarithm of initial pressure of arsine upon final pressure minus x. So by substituting the value, you'll be getting the K. Now different values are provided to you at different time intervals. You have 6.5, wherein the total pressure is given as 1.076. Then you have to find the x and substitute. Or if time is 8 hours, you have been given the total pressure as 1.1. By substituting, you can get again x to substitute here to find the value of K. But interesting fact is that the K is going to remain constant as it is the rate constant. When it is asked to prove that it is a first order reaction, you can find out the K at different time intervals and show that the value is remaining constant. And when you are asked to find the average rate constant, you have to take the average of all the K values that you obtain. In nature, a decay chain series starts with thorium and finally terminates at lead. A thorium ore sample was found to contain 8 into 10 to the power minus 5 milliliter of helium at STP and 5 into 10 to the power minus 7 gram of thorium 232. Then you have been asked to find the age of ore of the sample during this radioactive decay. And you are also provided with the T half of thorium as 1.39 into 10 to the power 10 year. Now we know that when thorium is undergoing decay to give you lead, as we can see 208, it is giving rise to the helium gas. Now in order to obtain the concerned difference, when we write here the helium particle and when we try to map it with the concerned equation, we will find that the beta particles also might have released during the course of the reaction. This I am saying because in order to map to the mass number of thorium, we already have a mass of 208 gram units and we need to get extra 24 units of mass. When I am writing here the 6 moles of alpha particle or helium gas which is obtained, the total mass number, because the mass contribution from beta particle is 0, the mass is 24 and 8, that is 32, matching. But when it comes to the atomic number, there is an increment or increase of 4 units by number 82 and 12, that is 94. Hence, in order to balance that, we are writing the beta particle also. But the concerned data which is provided to us is nothing to do with the beta particle, because we have been given the volume of helium gas which is released at STP and also the mass of thorium which is present after a certain period of time. Let us assume that the age of the ore is some T year, and here after this T time you are given that the volume of helium gas measured at STP is 8 into 10 to the power minus 5 milliliter. So therefore, I will be finding out the number of moles of helium gas which is present after the decomposition of thorium. The age of the ore is nothing but the decay time. And also it is given that the grams of thorium that are remaining after the decomposition is 5 into 10 to the power minus 7. Since we deal with the mole ratio, it is better to convert this mass quickly into the moles by dividing with the atomic weight. So this is the final mass of thorium that is remaining. Now to find the initial moles of the thorium that might have started during the beginning of reaction, you can see that for every 6 moles, 1 mole of thorium has reacted. For every 6 moles of helium produced, 1 mole of thorium reacted, or 1:1/6 is the mole ratio of helium and thorium in this nuclear decay. So for every this many moles of helium, I can anticipate the moles of thorium reacted to be 1/6 times of, because you can see they are in 6:1 mole ratio. This many mole of thorium might have reacted to produce that many moles of helium. Now this much is remaining. So the sum of these two will fetch you the initial mole of thorium in the reaction. Now you can use the relationship. This is the first order decay, lambda, that is 0.693 by T half of the reaction, which is provided to us 1.4 into 10 to the power 10 years approximately, is equal to 2.303 by time of decay log initial moles of the radioactive sample. These are the initial mole of the radioactive sample divided by the final moles of the sample. Now simplification of this will fetch you the value of T, and the answer for this question is 4.89 into 10 to the power 9 year. The specific rate constant for the decomposition of formic acid is 5.5 into 10 to the power minus 4 second inverse at 413 Kelvin. Calculate the specific rate constant at 458 Kelvin if the energy of activation is 2.37 into 10 to the power minus 4 calorie per mole. So in this case, we have once again the Arrhenius equation. Now the specific rate constant values are given to you at two different temperature. At higher temperature it is, you have to find out at higher temperature, that is log of K of 458 Kelvin is asked to be obtained, and now you are given the rate constant 413 Kelvin as 5.5 into 10 to the power minus 4 second inverse, which is equal to the energy of activation for you in this question is 2.37 into 10 to the power minus 4 calorie. 2.37 into 10 to the power minus 4 calorie. 2.303 into R value you substitute in calorie only, that is 2 into 1 by the initial temperature is being 413 and the final is 458. Now the simplification of this simple equation will fetch you the rate constant at 458 Kelvin, and the answer for this question is option B, that is 9.4 into 10 to the power minus 3 second inverse.